Mike, good morning.
Morning, Nick. How are you doing?
I'm doing great. How are you?
Doing pretty well.
Awesome. All right. Let's start with PA4. So PA4 is due Friday morning, 8 o'clock. Make sure it is submitted. Make sure it's named properly. Make sure I'm set up as a reporter by 8 a.m. Friday for grading for full points. So any questions on PA4?
I did have a question.
Cool.
So when you go to test this, when you're testing deleting of nodes, can we make the assumption that the node will always be there, the ones that you try to delete? Or do we need to assume that they might not be there?
Let me check the assignment.
I don't remember seeing it, but I could very well just miss that part.
Delete. This will delete the given using the exact. Make sure you understand any variation of everything other than these two commands. The delete command should either report success or plate not found. So yeah, you want to pick up the case where the plate's not in there and give that message.
Awesome, thanks.
Welcome. Somebody asked me in the other section. I don't talk about specific formatting for your traversal other than, I want one line, plate, angle brackets, name, colon, last name, comma, first. Somebody pointed out that in my example here I have a space between the names, and in the sample code I don't. And I don't specify that in words. So if you put a space in or you don't put a space in, either of those is acceptable. Okay, if you're trying to use the difference command to compare your output to the test code's output, then you don't want to put that space there, because that will make a difference. But I'm not going to take off points for that. So I think that was the only confusion on output format. So yeah, GDB and command line arguments. This is potentially tricky. So let's just write some test code here. So this program will accept command line arguments, and it will assume that there is at least one argument given, and it will print out what that argument is. So if I say go to hello, it will tell me, my argument was hello. So, for PA4, we're passing the name of a database file, so we want to be able to access that. So if you run this from GDB, and I try to say go to hello, and I run it, it tells me that, my argument was null. So inside GDB, so here's what you do. Just say GDB in the name of your program. Don't worry about specifying command line arguments here. GDB program name. But inside GDB, when you want to run it, put your command line arguments after the word run. And it'll run it, and it will pick up your arguments accordingly. So compile with the G flag, GDB program name, and then to start execution, say run space, and list your command line arguments. Does that make sense? And so if I say, you know, run, this is a test, and I've got a breakpoint here at main, it's telling me main was called, and I can actually see the value of argc and argv. Argc was 5. This is a test, and you know, the presumed first argument, which was the program name, and then argv is some location in memory. Right, if I look at argv, what is it? It's a pointer, right? If I print the thing that it points to, that's the first character of my path to my file. If I look at argv bracket 1, that's the word this. That's the word is. This is and this is test. Alright, cool. Next questions. So a couple of common issues that I'm seeing with PA4 from people who have been coming to office. Hey, welcome. A couple of common issues I've been seeing in people's code. The first one is allocating the wrong sized thing. So we can use typedef to avoid having to say struct node, struct node, struct node. So we can make some temporary variables that are struct node stars, and we can write our function add, which is a struct node star, and so on and so forth. When we want to allocate a node, we usually do size of struct node. Because a node is a bunch of things. It's a character plate array, it's a first name and a last name array, it's a pointer to a left and a right child, right? So a struct node has a whole bunch of stuff stored in it, so we use size of that struct to malloc space for a new node, so, you know, a new node. The possible trick here is if you typedef, and you typedef a struct node star to be something like node, like this, right? Well, now, you know, I can just say node root, and here I can say node temp, and here I can say node add. But be really careful in here. If I use uppercase node in here, I'm not allocating space for a struct node, I'm allocating space for a struct node pointer. And that's not enough space for a struct node. So if you're getting flakiness in your code, if you're seeing things kind of disappearing or overwriting or something like that, double check that you're not using typedef pointer to a struct node when you should actually just be using a struct node. So that's one gotcha, and I've seen that in multiple cases. The deeper gotcha has to do with the notion of pointers versus things pointed to. So if you're finding that all of your license plates have the same value, or that the root of your tree keeps changing, you know, the plate and the name keep changing to the latest plate that you read in, this is probably what's going on. So let's look at our main program, and it's got some temporary variables. So it's got a first name, a last name, and a plate. And somewhere along the way, you know, you read something in from the database file, and you maybe do an scanf to break it up into 3 strings and, you know, see if you had 3 fields in there and so on. And then somewhere along the way you say something like, you know, root equals add root plate first name last name and some other stuff. And your add function will, you know, do some kind of allocation. And it's natural to try to do something like this. So let's say we're calling this with, you know, plate first and last. All right, so what's happening in the memory of your computer? Got one memory. So your main program makes these variables called plate, first name, and last name. And the compiler linker decide where those are going to be stored in memory. And so maybe here at location 100, it stores plate. So plate, P-L-A-T-E, is synonymous with 100. If you were to print plate with a %D, you would see 100. It's a pointer, right? And the value of plate is the location in memory to which that points. And, you know, first name is somewhere else in memory, and last name is somewhere else in memory. All right, so when I call scanf, what am I passing? I'm passing plate. I'm passing the number 100 to the scanf function. And the scanf function, when it breaks apart the input and it says, oh, here's, you know, ABC123, that's the first string, I should load that here. It looks at plate and it says, you know, plate is 100, and so it writes the thing that it found into that location in memory. And then when the main program looks at plate and tries to print it out or something, it prints out, you know, ABC123. That all works great, okay? Here's the tricky part though. Suppose I call my add function and I'm passing plate. Remember, everything is passed by value, so since plate is equal to 100, when I get in here, this PL, this first argument to my add function, is 100. It's the address of the plate. Okay, now I say temp equals malloc, so I create some new location down here. Let's say this is location 4000, and that's the value of temp. And temp is what? It's a struct node, so it has a bunch of pointers. Plate, first name, last name, left, right. When I say temp plate equals PL, what does it do? It sets this plate pointer to 100. In other words, this is pointing right here. And if I print out some debugs and stuff like that, everything looks fine. Okay, what happens the next time that I call add? I've done another scanf, I've read another thing into plate, so plate has changed to, you know, DEF 567. Well, in my tree that I've already built, what does that root node point to? It points to DEF 567. My license plate has changed value inside my tree simply by my main program changing the value of its local variable plate. And so if I run into my code and I try to add a new node, I'm going to say temp equals malloc. So temp's going to be some new area. Maybe this is location 4100, and that's temp. And it allocates space for my pointers to plate, first name, last name, left, right. And now when I say temp plate equals PL, what was PL that was passed? It was 100. And so this node points up there also. So I have two nodes in my tree and they both have the same license plate. And now I go back to main and I read in the next line of my database and I scan that and I save the plate in plate, and maybe that's equal, you know, to XYZ 589. And now both of the nodes in my tree, their license plate is XYZ 589. All right. So if you're seeing this kind of behavior, go back and work on this inside your add function. So don't copy the pointer. What we want to do is we want to create a new area in memory in which we can store the plate for this node. So do something like temp arrow plate equals malloc. And make yourself a chunk of memory somewhere. Now, how much memory do we need to store the plate? However many characters are in the plate, and we find that by using stringlen. And don't use size of plate, right? Plate is a character pointer, its size is 8. It could point to, you know, the Guinness Book of Records, but the size of plate is 8. Right, or PL as I was calling it here. So use string length to find the length of a string. Never use size of on a variable, only use it on types, struct node, integer, double. Right? So find how many characters you need for that and add one more for the null terminator, because we want to copy the null terminator in here also. So when I do this, this is going to create a new chunk of memory somewhere. Maybe this is location 6000. And my plate is going to point down here. And now what I want to do is I want to copy these characters from here into here, including the null terminator. So I'd like to say template 0 equals PL0, template 1 equals PL1, template 2 equals PL2, and so on. And there's a function for doing that, that's string copy. It should have been PL, right? So this says read character from this string and copy it into that string, up to and including the null terminator. So do that right here, and then do the same thing for first and last name. And now you've got your own copy. And now if this changes to something else, right? Well, it doesn't matter, because this node, what's the plate? It's whatever's stored at this location in memory, and that value is going to remain intact. All right, so those are the main two issues I'm seeing. Mallocing the wrong amount of space because you used a type def and forgot it was a pointer, and not making a new memory location to store these strings associated with each node. So that's the bulk of where I'm seeing people running into issues right now. I've been seeing online that string copy is dangerous because there's no potential end. Is that true? Or if you are judicious, is it okay? Well, string copy is a loop, right? Basically, while input I is not null terminator, output I++ equals input I++, right? So if you don't know that there's a null terminator, this will copy, you know, a potentially unlimited amount of bytes from an input location to an output location. So yeah, theoretically, you know, if someone handed you a string and you didn't know that it was null terminated, you could overflow the thing that you're copying into. But, you know, since we're reading from, you know, an argument that was passed to us, and we believe our main program is going to send us a null terminated string, this is perfectly safe. And so this was the simplifying assumption that I said you could make, which is that the plates and names are no more than 40 characters. So in main, if you make these things, you know, 41 or 45 or 50, you're guaranteed to be safe. All right. Nobody has come to me with issues with freeing memory yet. So let's talk about freeing the memory of the tree once your program is done, because you want to get rid of all the memory that you allocate. And this is easier than freeing memory from a linked list, because we can do this recursively. So let's make a function. I'm going to call it free tree. And the goal is to free all of the memory associated with this tree. Every malloc that we did in building this thing. Well, if we think about this recursively, all we got to do is free the left subtree, and then free the right subtree, and then free the actual root node. How do we free the left subtree? Let's use our free tree function. We're writing it, it's a beautiful function. Let's go ahead and use it. And how do we free the right subtree? Use your free tree function. And then after you've freed everything on the left and the right, now go ahead and free the root node itself. And so that's a function that I'm calling free node. And how do we free a root node? Well, what's a node look like? It's got a plate, it's got a first name, it's got a last name, it's got a left child, and it's got a right child. And all of these will have been dynamically allocated. And they were allocated when the node was created. So if you have a node, you're guaranteed you've got 5 blocks of memory that need to be freed. So free each of those. So free the plate. Right? And then when you're done with all of that, free the node itself. Because these 5 fields are stored somewhere in memory that was allocated with malloc. So free the 5 fields, the 3 strings, and yeah, don't free the left and right. Just free the plate, the first name, and the last name. You don't need to free n arrow left because that happened before you got into the free node function. So free the plate, the first name and the last name, the 3 strings you created, and then free the node itself. And that's the only place where we actually free anything. And what's the one thing we're missing from this free tree function? I'll have to space up there for one more line. The base case where root is null, exactly. If the root's null, there's nothing to free, so return. And even if you're not freeing an empty tree, eventually this is going to be called with null because it's recursive. And if you think about what these lines are going to do, let's suppose that your tree looks like, A, B, C, D, E. And we say, I want to free this tree. Well, the first thing I'm going to do is I'm going to call free tree on this. And the first thing that free tree is going to do while the root's not null, it's going to call free tree on this. And the first thing free tree is going to do, since the root is not null, it's going to call free tree on D's left child, which is null. And in that call, it's going to say if the root is null, return. So that call to free this thing's left child will come back right away, and the call to free the right child will come back similarly. And then it will say free the root node, and that'll call free node on D. and that will free the 3 strings inside here, and finally it will release that node from memory. So even though I called free tree with this whole tree containing 5 nodes, the first thing it did was release that node. And if you work through that, the next thing it will do is release that, and then node B, and then it'll come over here and release node C, and then the last thing it does is it'll actually release the root. So that's kind of the recursive view. All right, any questions on that? And Valgrind will help you with that. Again, put a -G when you compile your code, and Valgrind will give you line numbers if it's finding issues. Usually the issues people run into here is just with trying to free things at the very end. Alright, so, question in chat about the left node right, for example, traversal function. So you've heard me say that in general we don't want to print things from these functions. Traverse is an exception to that. For PA4, your traverse function should actually print the contents of the tree using, you know, the output order described. So that's a case where we're actually going to do printing from the traverse function, lnr, etc. But search and delete and add, all of that, you shouldn't be printing anything from there. If there's an error, don't print it from that function. Use the return value to indicate an error. For example, if you can't delete a plate, you're supposed to return a 0 saying you didn't succeed. Your main program picks that up and prints it out. If you're searching for a plate, your search function populates the first and last fields that you passed to search, and then your main program can print those out if it wants. Right? Don't print stuff from your functions in general, except for your traversal functions. So your traverse functions can go ahead and do some printing. So what's left node right look like? Well, traverse the left subtree. Print the root node data. Traverse the right subtree. And the same base case, if t is null, there's nothing to see here, so just return. Alright, pre-order traversal, node left right. If t is null, return. Otherwise, the N says print the root data first, and then traverse the left, and then traverse the right. And the post order, left right node, so if the root is null, return. Otherwise, do the traversal of the left, do the traversal of the right, and then print the root data. Exactly the same code, except that, you know, in order we print in the middle, pre-order we print first, post-order we print last. And a couple of logistical comments here. First one, right, since we're not just printing integers, right, this is going to be something more than you know, an integer print. But, you know, you're going to print the plate, the first name, the last name, in some kind of formatting that's described in the assignment. The other thing is, if you're copying and pasting, which is good, right, since this code and this code look almost exactly like this, you can copy this code into here. Don't just make an exact copy of this and move print in the beginning, because notice inside here, I'm calling NLR. And inside here, I'm calling LRN. And in my original code, I was calling LNR. And don't confuse those. Don't call LNR inside your NLR routine. Don't call LNR inside your LRN routine. Right? It's a really easy mistake to make, but then your traversal order comes out, different from what it should, and you lose points. So copy paste is good, but step back, make sure that what you're doing is making sense. We haven't really played much with pre-order and post-order. But here's the tree, so we know if we do in order, right, we'll basically go all the way to the left. Print the root node, go to the right, pop up to the original root, come down to the right subtree, go to the left, print out the root. If we go pre-order, node left, right, first we're going to print the 20, then we're going to traverse the left subtree, so we start with the 10, then we're going to traverse the left subtree and start with the 5, then do its children, which don't exist. Then we'll pop up here, we did the node in the left, so then we're going to do the right subtree. And now we've done the root node of this, and we've done the whole subtree on the left, so now we're going to do the subtree on the right, which is going to start with a 40, and then go to the subtree below that on the left. So there's the pre-order, which is not really any kind of noticeable order at all. And left-right node is going to go 5, 15, 10, 30, 40, 20, if I'm doing that correctly in my head. So those don't actually come out in some kind of understandable order. However, if we did kind of a reverse in order, right node left, right, this would go down to the right as far as it could, print out the root node, go to the left, done with the right, print out the root node, go to the left, which will start off by going to the right, print out the root node, and go to the left. So that will give us descending order. But these two search orders, pre-order and post-order, are a little more mysterious. And we'll say some things about those. Now, because I just made a note to say some things about those. All right. So for the search function, I'm confused on the part that says populate first and last. Does that have to do with the first and last nodes malloc in the add function? Not exactly. So the search function actually has two purposes. It searches your tree to tell you if a plate is contained in there or not. But additionally, if the plate is in the tree, it tells you what the name is associated with that plate. So if you look at the prototype for search, you pass it the root of the tree, that's pretty obvious. You pass it the plate that you're looking for, and then you pass two other character arrays, first and last. And the behavior of the function is search for the plate, and if it's found, we're going to return a 1. If it's not found, we're going to return a 0. But in addition to the return value, which is an int, if it finds the plate, when you come back from the call to search, this variable should now have the first name associated with that plate. And this variable should have the last name associated with the plate. So if I want to search for, a plate, right? So I need to have some temporary variables. So I'll have some character arrays, first name, last name, that can hold 50 characters. I call my search function. I give it the root of the tree, the plate I'm looking for, and these two variables, right? Remember, these are pointers to characters. When I come back, if I find that search returned a 1, then Fn and Ln will be the names associated with that plate, and I can go ahead and I can print them or do whatever it is I want to do. So the search function, start at the root, go down, look for the license plate. When you find it, you're going to return a 1, but before you return, take the first name that you find in that node and copy it into this variable. And take the last name that you found in that node and copy it into this variable. And how you do that, just use string copy. There's already space allocated for those strings, so we don't want to do a malloc, right? Fn will be pointing to some area of memory where there's, presumably 40 characters available. And so we just string copy from, node arrow first name, for example, into that variable. So that's what that business is of populate the first and last, and then return a 1. So that's just copying into these. And it's the same thing that happens when you call scanf, right? You pass it the address of a character array, and it copies characters into there. So you send a character array into search, not an empty pointer. Right, yeah. If you send an empty pointer, you'll segfault. So, so in your main program, have some character arrays with space allocated, right? So I allocated 50 spots here, and then just pass those arrays to your search function. And it's just a way to pass information back. Since search is already returning an integer, right? Then we need some other way to get the actual name, so we just pass those as arguments. Alright, good, or better. Alright, let's talk about merge sort. So I mentioned yesterday that when I would grade assignments, that were turned in physically on paper, I seem to do an insertion sort. So, I take the first paper and I look at the name on top, and, if it's the first paper, that just goes in my output pile. Then I take the second paper. If that name comes before the first, I put it on top. If it comes after the first, I put it on bottom. And I take the third one, and maybe that name goes in between the first two that I already got, so I put it in between. And I'm basically pulling, papers off the top of the pile, and I'm inserting them into my output pile in the correct place. And it's pretty easy to do this, right? I get a paper and the last name starts with G, and I just flip through here, and here's an A and an A and an F, and there's a T, so it goes, in between the F and the T. That's not a bad approach, and if I'm doing, 10 papers, that doesn't take long. But, particularly fall quarter, I might have 60-some students in my class, and if I'm we used to combine sections, so I'd have, 60 names alphabetized in the grade book that I had to enter grades into, so I wanted to sort the homeworks alphabetically. So, the first few names that you pull off, well, you've got an output pile with 3 or 4 names. That's not hard to put them in the right spot. If you have 60 names, that last paper, you have to find where it goes in an output pile of 59 names. That's basically 59 comparisons. So we said insertion sort is order n squared. What does that actually mean? Well, for typical cases, this is actually going to be n squared over 2. So if 60 papers, this is going to be 3600 over 2. 1800. So I'm doing about 2,000 comparisons of names. I'm alphabetizing 2,000 pairs of names to sort this stack of papers. Right? That's where n squared starts to hurt. And I realized, you know, if I can do this in 5 seconds, that's 10,000 seconds. That's like 3.5 hours I'm spending just alphabetizing papers. Right? So, so what I start doing usually is when I have, you know, more than 15 papers, for example, I'll just grab a chunk of these and I'll alphabetize them. And I'll grab the next chunk and alphabetize them. And now I've got, you know, 3 or 4 piles that are alphabetized, and now I put those together. Okay? This is the essential behavior of a merge sort. So the idea is sorting small things might be doable, but sorting large things might take longer. So let's merge sort a set of data. All right. So step 1, split the data in half. Alright, so that's breaking my paper pile into 2 subpiles. Step 2, which uses some sort of magic, let's sort this left pile. And let's sort the right pile. Step 3, let's merge these 2 piles into a sorted output pile. And this is pretty easy to do. So I know that this is sorted smallest to largest, this is sorted smallest to largest. I'm going to pull things out of these 2 arrays and add them to my output. And what I'm going to do at each step is I'm simply going to take the smallest thing between this and add that to my output. So I compare 2 to 5, 2 is smaller, so I'm going to put 2 in my output. And now that's removed from here. So now I'm going to compare the first thing in this list, 4, with the first thing in this list, 5. 4 is smaller, that goes in my output. And it's removed from this list. Now I'm going to compare the smallest thing here, which is a 6, with the smallest here is a 5. 5 is smaller. So I'm going to put the 5 over here. And now the 5 is gone. So now I have a 6 and 11 here. I have a 12, 18, 25 over there. So I compare the first thing, 6 and 12. 6 is smaller. So that's my next output value. Now I compare an 11 to a 12. 11 is smaller. So 11 is my next output value. And now I've hit an edge case. I have nothing left in this side of my list. This stack is empty. So at this point, I can just flush out what's left in this stack and just copy these directly to my output pile. And guess what? My whole list is sorted now. 2, 4, 5, 6, 11, 12, 18, 25. So merge sort is 3 steps. Split your input into 2 halves, roughly. If it's an odd number of things, they'll be off by 1. But split it roughly in half, and then do some kind of magic to sort each of those halves, and then interleave them, merge them into a final output list. So splitting in half, right, that really takes no time. This merge process, what's the order of complexity of the merge step, do you think? If I have n pieces of data, roughly how much work does it take to interleave those into a single output array? You think it's n squared, log n? It's n, right? However big these are, right, I'm going to compare the first 2, I'm going to compare 2 more, I'm going to compare 2 more, and 2 more, and 2 more, and 2 more. I'm going to basically go through n pieces of data. So the merge step is easy. So the real question is, What's the magic step here? How are we going to sort these sublists? So any ideas? We didn't get to this in the first section, but we got a couple of minutes here. So what's a good way to sort those sublists? Merge sort. Perfect. Let's call this handy thing called a merge sort. And just hand each of those sublists to it. There we go. So you almost don't have to write anything. There's no sorting involved in here. The only thing you actually code is this interleaving. And this is just go through two arrays, compare the top of each array, pick the smallest, add that to your output. But it ends up sorting, and it ends up sorting really efficiently. So how many times do we call this merge sort? Well, each time that we go through this algorithm, we cut our list in half, so it's going to be roughly log n times that we have to recurse. And so this will end up being an n log n. It's slower than O n, but most sorts are. An order n sort is pretty elusive. Generally, n log n is kind of the best we do until we get into strange parallelism and stuff. Alright, so that's a nice example of recursion, right? How do we merge sort? Split your list in half, merge sort each half, interleave them together. So we'll play with that a little more tomorrow. We'll look at some other sorts, radix sort, and then we'll talk about heaps. Alright, cool. Have a good one. I will see you next time.